Right. Well, today we are going to start with the infamous algorithm sprint. So I'm sure you're all very excited and maybe a little intimidated of this. I just want to reassure you that algorithms can be tough, but I don't think that this sprint has to be stressful. All right, we're gonna walk you through we have a lot of stuff to go over, but we're gonna walk you through it, and I think as long as you put in the work, you'll all be just fine. Let me see. So to confirm, do we have no iOS students and no data science students in this cohort? We don't. They're not just shy. All right, how many people do we have in this? Okay, well, 62 people voted for time zone, 56 voted for main track, and 58 voted for beverage. So there's a few people who haven't voted. I'm wondering if there's any iOS or DS people out there who are shy. There should be iOS. There should be. I know that there's a lot of scheduling weirdness that came with a recent change to 4-week sprints, 4-week units. Sorry. So we have this mini group CS20, which was web, or a lot of like web 18 students, or they're called like web 18.5, and I think there's a big mix there. So I think there's a lot of um, scheduling things going on here. But this seems like a pretty big group, right? We have 78 people in Slack, 68 people voting. So, all right, well, maybe not. Maybe there's no iOS people here, but I'm glad we have some Android folks holding down the fort for mobile, to make sure that keep the web students honest and keep us honest too, to make sure that we're talking about these generalized concepts. I think one of the cool things about computer science is that the things that we learn here will apply between all different tracks. So if you're in web and you happen to you want to go into mobile later, whether that's through React Native, whether that's through something like Unity, or whether through learning the native language, these computer science topics will absolutely still apply. So the things you learn here, unlike learning something like React. The coding principles you'll learn in React are very important. Of course, that's going to be your bread and butter. That's what's going to get you the job. But React wasn't here 10 years ago. It's questionable whether it'll be around 10 years from now. But in the form of legacy code, it's definitely not going to be the hottest thing 10 years from now. So at that time, things like computer science, things like the things we're going to learn here in algorithms, these will definitely still apply. So I hope that you all will get a lot out of this week. Cool, but it seems like some of you are getting into React Native already. So that's really awesome. Okay, so I'm gonna try, since this is a pretty big group, I'm gonna try this tool called Slido. I don't know if you have used this before. But basically, this is a way to ask anonymous questions. Since we have a lot of people, sometimes with big groups, I lose track of Slack, and if you type a question here, I might miss it. So you can add your anonymous questions here. It works like this. What is an algorithm? You can put your name if you want, but you can also leave it anonymous and send. And I will see this question pop up here. It'll say, "What is an algorithm?" And then, maybe I'll be lecturing. I'll be talking about something else. We'll be talking about Big O. We'll be talking about sorting, and then I'll come back to here, and I'll see a question. Oh, what is an algorithm? And I can answer this here. So an algorithm is it's just an algorithm, to answer my own question, is a list of steps or procedures or rules to perform something, to perform a task. It doesn't have to be, it can be anything, right? There's an algorithm for baking cookies, which is also known as a recipe. right? That algorithm may be, all right, we get this much sugar, get this much flour, get this much shortening, mix it together in a bowl, add some chocolate chips, throw it in the oven at this temperature for this many minutes, right? That's an algorithm. Crossing the street safely. Step to the sidewalk, look to the left, look to the right. If the left is safe, I guess if left is safe, look to the right. If right is safe, walk forward until you hit the other end of the curb, right? That's an algorithm. Algorithms are every single line of code you've written in your life is an algorithm, even if it's very, 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 very simple. Even if it's just create a div, like display, I guess you can say display hello world on the screen. Maybe you put that in a div. That's an algorithm. Even though it's one line, it's an algorithm. So when we talk about we're learning Algorithms Week. I think a lot of people think of algorithms as these really tough, really tricky challenges / puzzles that are really, really hard. And I want to demystify that if possible. So we're going to be going through some algorithms that are very hard, but we're also going to be looking at some very simple algorithms. And we're going to see that the steps we use to solve them can be applied to every algorithm, whether it's simple, whether it's very complex. And as you've already known, as you've already been introduced, that method that we're going to use to attack these algorithms is Polya's problem-solving principles. Now I'm going to repeat those right now because you're going to be hearing these repeated over and over and over again throughout the next few weeks in CS. These steps apply to every single problem, technical or non-technical, interview or working on a problem in your jobs or for your projects. It really applies to anything. And those 4 steps, of course, are step 1, understand the problem. Step 1, understand the problem. Now, this is probably the hardest step. This is probably the hardest step for most people. This is also a step that most people probably skip over most of the time. And when you're having trouble with writing code, it's probably because you did not put enough time into step 1. And we'll be looking into that. Step 2, come up with a plan. Once you understand the problem, you should come up with a plan of attack. Now, sometimes the plan is obvious. Sometimes sometimes the planning step can take 10 seconds. But most of the time, you'll save a lot of headaches by spending a little bit more time on that planning stage. And we'll take a look at that this week as well. Step 3 is taking a first pass at the solution. That means writing code. Again, writing code is only step 3. This is actually the easiest step in most cases. If you really understand the problem, if you've come up with a good plan, then writing the code itself should actually be very, very simple. And then step 4 is to reflect on your solution, to iterate and improve. And that's a lot of the stuff we're going to talk about here this week. Will be focused around that step 4. What does it mean to iterate and improve? Well, you can look at efficiency, things like time complexity. That's what we're going to be talking about today. You can also iterate for readability, and that's actually probably the best way to iterate. Usually by increasing the readability, you will also increase the efficiency. So those steps, number 1, come up with a plan. Sorry, number 1, understand the problem. Number 2, come up with a plan. Number 3, take a first pass at the solution. And step 4, reflect, iterate, and improve your solutions. These 4 simple steps can be used to solve any algorithm in existence. And this week we're going to be examining many, many different kinds of problems, and you'll be able to apply these steps to all types. Again, from easy to very, very difficult. If you remember these steps, you will always be able to make progress. Okay, let's see. What do we got here? Waffles. What is an algorithm? What is cheese? So they're more over-glorified if statements. Let's see. If statements can definitely be part of algorithms. I don't know if they're over-glorified or properly glorified. I think if statements are very powerful. I don't know. I don't know. There's a lot of different things you can do with algorithms. So let's jump in. Unity and GIMP looks like I make games. Yes, I do actually, and you can see some of those in my in my portfolio if you're interested. Yeah, I was lurking in your channel last week, and I saw a lot of a fun discussion about games. So you know, I was really excited to jump in with you. We can talk about some of that as we go along. Interestingly enough, all three of us, in all three of the instructors, the full-time instructors in CS, have all worked in the games industry. That's me, Beej, and Brian Doyle, who you'll be seeing next week. And if you're looking, you know, I think again, computer science is kind of intimidating. People think, oh, I'm learning binary search trees and these algorithms and big O. Yes, we learn all of that, but why do we need to do that? Well, if you don't necessarily need to do that if all you want to do is very, very simple things, right? Like, all right, I want to create a login form, and I want to make the buttons have rounded edges, and I'm going to make this blue, and I'm going to give it a margin or a padding of 10 pixels. Sure, you don't really need CS for that. But if you want to do anything more complex, like, for example, a game, you will need to write some more complex algorithms. You will need to worry about efficiency, and things like computer science will definitely come in. So those of you who are interested in games, even if you're not trying to work in the games industry, but if you're looking to make games as a hobby, which I do a lot, computer science is very, very important to know, because that will let you stretch your limits, right? Whether that's rendering more polygons on the screen or making some complex game mechanic that fits whatever the vision is in your head. You will want to make use of some of these algorithms. What exactly is big O notation? Great question, and that's actually exactly what we're going to be talking about today. Okay, let's talk about more about the games industry stuff maybe on Friday, because we have a lot to go through this weekend, and I have a lot to talk to say about that. But yeah, we'll save that for the end of the week. Okay, big O notation is a measurement of the efficiency of your algorithm. Yes, that is true. Let's before we talk about that, let's look at an example of some code. Okay, first topic for today is actually, I think why don't we just start with big O, since that's where we are. Okay, yes, big O notation is a measurement of the efficiency of your algorithm. The way we measure that is using things like O of n, O of n log n, O of n squared, O of 1, things like that. All right, what does that all mean? Well, the way I want to start is with some Python code that I wrote a while ago, but that I think still fits. Okay, so here I wrote the secret to coding. All right, now we can just paste this into Python. Python 3. Whoops. All right, so if we print out the secret to coding here, we say beautiful code is both elegant and efficient. Elegant code means concise, easy to read, easy to understand, easy to maintain, and easy to modify. Efficient means minimal CPU operations and minimal memory and storage requirements. Okay, so elegant, we can define this as easy for humans to read, easy for humans to understand, easy for humans to maintain, and easy for humans to modify. Okay, this is really, really important. Yes, we write code for computers, and that's what the second half is. That's what the second part is, efficient code. We want to be efficient in our operations. We want to be efficient in our memory and storage requirements. We don't want our computers to have to work any harder than they need to. But maybe more important is writing elegant code, code that humans can read, code that humans can understand. Okay, so we have this code here too. Okay, it says the same thing. I guess it's not the same. This is concise. But other than that, they should be the same. Minimal CPU operations. So which of this code is better? Which of these codes are better? Which of these functions, I should say, are better? Okay, trick question. We will get into which is better. I have a definitive answer. They both do the same thing, but I do have a definitive answer. Okay, 2, 1, 1, 1. Okay, 1 is more readable. 2 is probably slightly more efficient. But which is more important? I would say number 1 is maybe more elegant. Number 2 is more efficient since we're only doing one print statement. But in order to do this, in order to make a definitive decision about which is best, and this is getting to step 4, right? We're skipping ahead in Poly a little bit, and we're getting to step 4. How would you make your code better? In this spirit, I also want to type in import this. If you haven't tried this in Python yet, import this gives you the Zen of Python. Now this is Python's philosophy. Those of you who write JavaScripts or in Android, do you write more Java or do you write Kotlin? I heard it changed, but what is your main language there that you've been coding in? I guess this is also like for iOS, do you write Swift or Objective-C? I think they do a little bit of both. Okay, so mostly in Android, you're doing Kotlin. Okay, that's a little tougher for me. And Swift, what? Swift for Android? Okay, well, because I know Java, I don't know any Kotlin, so I don't know. I may refer to Java a bit, if that's what you understand, but I know nothing about Kotlin, so okay, that's cool. Okay, anyway, this is the philosophy of Python. Now, Python, as you saw last week in Intro to Python, Python focuses a lot on readability. The syntax is made to be almost human readable. The syntax is almost like writing pseudocode, in that Python removes a lot of things like curly braces and semicolons. And I think you're all used to writing for loops, like something like for int I equals 0, I is less than array dot length, I plus plus, all right, and then prints array of I, right? You're probably used to doing something like this, which is fine. This is all very readable for coders, for computers as well. But this is not very much like English, right? Like for int I equals 0 while I is less than array dot length, I plus plus. What does that even mean? Much easier to say something like for element in array prints elements, right? This is very, very human readable. This is almost like how you would write it out in a sentence, and this is exactly why we like to use this for algorithms. Very, very readable. So yes, we're focusing on efficiency, but I also want to make sure we're focusing on readability as well, so we don't forget all of that. Okay, so with all of that said, let's jump into Big O. Okay, so in order to demonstrate this, I have some code here. I made a list called animals. There's 10 items here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're going to be doing some different things with this. Now, what do we mean by Big O? What do we mean by time complexity? Okay, now there's two different elements with Big O: time complexity and space complexity. We're going to start by talking about time complexity, and then we'll touch on space complexity briefly. Okay, we'll touch on space complexity briefly in the end. It's actually fairly simple if you understand time complexity. All right, what do we mean by complexity? Well, what we mean by complexity and Big O is how does the performance of your code scale based on the size of your inputs. Okay, this is really important. You can look at some code and say how fast is this? How slow is this? You can even time it, right? You can set a timer, run some code, and then do the stop time. But that's problematic for a variety of reasons. One is that computers tend to have a lot of things running. Sometimes your code can run slow for reasons unrelated to the code, and also when we talk about performance, we really care about how it scales, right? Computers can do almost anything really, really quickly, but when it has to do that thing many, many, many times, that's when you start to get slow. For example, if it can do something in 1 millisecond, that's fine. But if you have to do if you have to do it 1,000 times, now it takes 1 whole second, right? If you have to do it 1,000,000 times, then it takes 1,000 seconds. And now we're getting into things that take a really long time. So that's what we care about. We care about how things scale based on the size of the inputs. This is why you have an app that runs fine when you have 5 users, but what happens when you have 5,000 users? That's what we care about with complexity. Okay, so we use what's called big O notation, and in here we have things like O of 1, O of n, O of n squared. Now what these are, this is the shape of the curve. This is the shape of the performance curve, right? Those of you who maybe it's been a while since you took algebra in 9th grade or whatever. It may be a little bit rusty. Some of you out there are very averse to math, which is fine. We're not going to have to do too much calculation here. All right, you're not going to have to do a whole lot of algebra. But what you will need to remember, especially if you're not very comfortable with math, you don't need to memorize exactly what these are or how to calculate them, but you do need to memorize the shape of those curves. Okay, and here's what I mean by that. You'll need to know that O of n looks like this. You'll need to know that O of n squared looks like this, and O of 1 and O of log n looks like this. Okay, remember these shapes. We're going to get into how they work, but you'll want to remember this. This is performance. Okay, so as your inputs get bigger, this is how long it takes. Now, as you can see, things like O of n, that means when your inputs get higher, performance gets worse. O of n squared, as your numbers get higher, performance gets bad really, really fast. And for things like O of log n and O of 1, performance stays pretty good even as your inputs get large. All right, so we're going to come back to this picture many times, but again, remember, you're going to want to remember the shapes of these curves. And if even that is hard, you can remember this as well. You can say O of n squared is bad, O of n log n is all right, O of n is okay, is pretty good, and then O of n log n is this orange, and O of log n and O of 1 are both pretty good. All right, so what does all that mean? Well, we have some code. Let me copy paste this into our Python. Okay, so again, we have this list of animals. We have 10 animals in here. Now let's say we wanted to write a function that says get all animals. All this does is it returns the name of our animals, right? So we type get animals, and it returns our list. Now, the time complexity of this is going to be O of 1. What this means is it's constant. It means doesn't matter how big our list is, doesn't matter if we have 1 animal, doesn't matter if we have 1 billion animals. In order to get the name of all animals, this is an O of 1 operation. What that means, it's what's called constant. Now, the reason this is constant is that all we're doing is we're returning a pointer to the start of our list, right? Now, this is a little bit unintuitive, maybe, because you think, wait, if you're asking for a small list versus a big list, shouldn't the small list be faster? Well, because we're only pointing to the start of the list, it's actually not. It actually doesn't matter. So this is a constant time operation. Again, it happens. Doesn't matter if you have a big list, doesn't matter if you have a small list. All you're doing is one operation, which is returning the start of this list. Let me drop these links in for you so you can see them. Big O cheat sheet is a really great resource, especially when you get into data structures. So data structures and algorithms are very, very closely related, as we will see. That's why we teach them consecutively. But these complexities, time and space complexities, apply to each of these different data structures, and that's actually why we learn them. Right? There's different trade-offs. There's different costs and benefits for each data structure we use. So it's good to learn different ones. This week, we're looking, well, for the first 2 days, we're going to be looking at sorts. So there's also some trade-offs between different sorting algorithms. This is why we're starting here with big O. Okay, so again, getting all animals, this is going to be an O of 1, a constant time operation. Don't worry if you're confused. We're going to circle back and go over these again. Okay, now we have an O of n operation. This is also what's known as linear. Linear means like a line. And as you can see, this green line is the O of n operation, right? It's a straight line. That means as you add more inputs, the performance will increase linearly. What does that mean? Well, let's say we wanted to return a function that counted the number of animals in our list. We have this function called count animals. We call it, and it gives us the number 10. Okay, now how are we doing this? Well, we initialize this number of animals to 0. We do for animal in animals, number of animals plus equals 1, and then we return the number of animals. Okay, so how many operations are we doing? We have 10 animals, so we need to do this counts 10 times, right? That's what we mean by O of n. We have our input is size n, and for each of these inputs, we need to do something. Right? And that something is incrementing our counter by 1. Now, if we had 1 animal, then we would only need to do this 1 time. If we had 1,000 animals, we would need to do this count 1,000 times. If we had 10,000 animals, we would need to do this 10,000 times. So the number of operations we need to do is linear. We need to do okay. So we can also do something like print. To see that, we can do print num animals equals num animals. And if we print this, count animals, you can see we're printing out these things, right? So now, instead of just doing one thing, we're doing 2 things, right? Now, instead of just doing one thing, we're doing 2 things. So does that mean we have something like 2n, big O of 2n? No, that's correct. They're constants, yes. So when we do something like this, we always drop the constants. Why is that? It's because it doesn't really matter if a computer does 1 thing versus 5 things. All we care about is the shape of the curve, right? All we care is this a straight line that's linear, or is it an exponential curve, or is it a logarithmic curve, right? That's all we care about is the shape. We don't care about the specific like calculations. Like we're never going to say how many operations is your computer doing, because the truth is, even if you're just incrementing something by 1, this is just 1 line of code. There's multiple operations underneath the hood that your computer needs to do. Like it'll need to set a register to this, set this register to this, it'll need to add this, it'll need to write that register to memory, it'll need to do a jump to do the loop, right? There's going to be multiple operations there. But we just count it as 1. So for complexity, we always drop the constants, right? So this even though this is still going to be O of n. Yeah, exactly. So again, remember, we always drop constants. We always drop constant coefficients. So even though this is O of 1, this might be like O of 1 million, but we just call this O of 1. I know I just wrote 1,000, not a million. Okay, let's do some other O of n's. Returns, here's a function that takes our list of animals and then returns each animals with the letter lowercase. As you can see, we're doing, where are we at? As you can see, we are doing 2 things here, right? We have, here's our lowercase animals list, our animal index. For each animal, we increment the index by 1, and we set our new lowercase animals to be lowered. So if we do this, whoops. If we run this, it's all of our animals lowercased, and this is also an O of n, even though we're doing 2 operations here. And I think actually this just set our original code to be lowercase because we were passing by reference, not by value. Okay, so let's make these big again. Okay, we have this function has animal. Has animal returns true if the animal is in the list, false otherwise. Okay, what is the time? Okay, what if we're looking for an animal in our list of animals? What is the time complexity of this? How many, put another way, how many operations, how many comparisons does our code need to do in order to find our animals? So we have 10 animals in our list. What will be, how many operations we need to find an animal? 10? Max 10. Up to 10? How about on average? On average, how many will we need to look through? 5, 3-ish, 6? 11? Okay, depends. Depends, yes. It does depend. On average, if we're just assuming a totally random distribution, on average, we're gonna have to look through 5. I guess assuming that the item is in our list. If the item is not in our list, we're gonna have to look through all 10, right? And we can see how that works. We can see how that works here. Let's do something like this. Num comparisons equals 0 and print num comparisons plus equals 1, and let's print comparisons. All right, so let's see if we have flamingo. All right, so we had to do 6 comparisons here, and we found it was true. All right, what if we want to do, what if we want to find dog? Okay, dog, we had to do 10 comparisons, and it was not in our list, right? What if we wanted to find duck? Duck, we only need 1 comparison, true. Okay, so we had 6, we had 10, and we had 1. Right, so what is the time complexity of this if it depends on if the item is in our list or not? O of n. Best case complexity would be O of 1, even though best case doesn't really matter. O of n, it's always a worst case scenario. O of n, we have a few guesses here. Okay, so a lot of correct answers here, a lot of good insights here. Best case complexity would be O of 1. Yes, best case being if the item is the first item in our list, like we had here with duck. O of n. All right, worst case I guess would be we have to look through every single thing, which would be O of n. Now average case would be we have to look through half of our items, right? I guess assuming that the item is in there. But like if we're looking for flamingo, we would only have to look through 6. So we still consider this O of n for best and average case. Sorry, for worst and average case. And this is why when we look at this, we have big O. Big O is worst case. We have big omega. Big omega is best case, and big theta is average case. Now we don't really, when we talk about this, we usually just say big O. Big O we kind of use to refer to all of these things. If you want to be specific, and by that I mean like maybe if you're getting a PhD in CS, you'll have to look at these things in very specific terms. But generally, we just say big O, right? We just say big O. What is the big O of this? And we usually mean interchangeably average and worst case. Like for example, something like a hash table. Hash tables are big O of 1 for insertion or deletion, even though technically we're actually saying big theta of 1. But I don't know anyone who says big theta. All right, I think we all just say big O. But what we're really looking for is like, what is the order of complexity? So so for this one, we'll look at the average case or the worst case, which gives us O of n. The average case, since we have to look through half of them, would be O of n over 2, right? Since we're looking through half, which is the same as O of 0.5 times n. And since we drop the constant coefficient, this is just equal to O of n. So we're just going to call this O of n. I don't know. I have a CS degree, and I don't say O of theta. I don't even remember what that is. I don't remember. I always forget between omega, theta, and O. So I just say big O. People will know what you mean. People will know what you mean. Okay, and unless you're doing something very specific, people are just generally looking for big O. Now, to pause for a second, why are we learning this? We learn this for communication, right? We learn this so we can talk about code, so we can look at it and improve our own code, right? So in order to know how to improve it, we need to know how to measure it. So this is how we measure performance. If you want to improve the efficiency of your code, this is what you want to do. And again, when we talk about efficiency, we look at big O, because the difference, I saw a question up here, isn't, yes, you have O of n and O of 15n. Isn't O of n more efficient than O of 15n? Yes, it is. But the way computers usually work is that when things are very small, they scale. They're very differences like that don't mean that much, right? And what I mean by that is if you have something that takes 1 millisecond versus 15 milliseconds, that's like as a human, you really can't even notice that, right? Like we can't tell the difference between 1 and 15 milliseconds. Now, what we can tell the difference is between 1 millisecond and 1,000 seconds, all right? And that's the difference between an O of n and an O of n squared, is the differences get really big, really fast. Just like these pictures of our curves. When you have an O of n squared, things get really big, really fast. And we'll see some examples of how these performances can blow up. Okay, let's see how we're doing on time. We can keep moving. Shuffle does the same thing. It takes each item and it swaps it with a random item. This is known as the Fisher-Yates shuffling algorithm, which we're going to be going into more in a few weeks. But let's so that's O of n. O of n is pretty simple. It means that for every item in your inputs, every item in your list, you do something, right? That's very common. All right, we need to take all of our items and do something to it. Maybe that's print it, maybe that's display it in a table, or display it in a list, or make it capital, or do something. That's O of n. You usually know you have an O of n because you have a for loop. You'll notice here, for loop. For animal and animals. This is a good signifier that you're doing an O of n operation. Okay, now we have an O of n squared. Print animal pairs. Let's take a look at what we're doing here. Okay, so we wrote this code, print animal pairs. So this is taking each of our animal and saying what are all of the combinations that we can have with these two animals. So you can have a duck and a duck and a jackal, a duck and a hippo, a duck and an aardvark, and so on and so on and so on. You can see we have for each animal, we do for each animal we need to pair it up with each other animal, and then we print it here. Right? This is this we can see our number of operations here. Num operations equals 0. Num operations plus equals 1, and then let's just add this here. Num operations. Okay. Does anybody have an idea? Anybody have a guess about what the number of operations will be for the last one? How many total operations are we going to call here? 100. Let's see. 100. Exactly right. 100. 10 times 10. So this is a very basic O of n squared. What does that mean? we have an O of n here with our first for loop, but within that we have another O of n. So yes, this is going to be an O of n, and for each of those n, we do n things. So this is called O of n squared. As you can see, if we add another animal, to this, we would get. So let me see. How many do we have? H, I, J, K. So let's add kangaroo. Kangaroo. Now we're going to get 121. Print animal pairs. 121. So again, the number of operations here grows very, 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 very fast. Okay, if we do something like, I'm not going to do animal list, but let's just do numbers. Equals list range. Let's do 100. So let's say we have 100 different animals, and our animals are just numbers. Okay, now, well, when we do this, we're going to have to do 100 times 100, which equals 10,000. Print animal pairs. So we have 10. We had to do 10,000 things here. So as you can see, just by adding, multiplying this by 10, we multiplied the number of operations we had to do by over 1,000. Okay, and that's what we mean by, by 100. We had to multiply it by 100. So that's what we mean by O of n squared. Yes, go through, for each item here, we need to do 11 things. And we need to do it 11 times. So that's 11 times 11. No, you still want to do O of n squared, because there is still a difference between O of n squared and O of n cubed, which we'll look at. I'm going to get rid of this kangaroo. Just keep it nice and simple with our tens. And we can see that with here. Oh, here's an O of n cubed. Print, this should be print animal triples. Animal. This is going to be the same thing. We have a for loop and a for loop and a for loop. We have O of n cubed. If we do our operations here, we will see that it equals 10 times 10 times 10, which is 1,000. Should be 1,000. Oops. No, it's 0. That's operations plus equals 1. And we get 1,000. So how do we know this? Because we have a for loop and a for loop and a for loop. N cubed, as you can see, we only have 10 items and we're already doing 10,000 things. Okay, how, if each of these operations took a millisecond, now our code is going to take 1 second to run. Now, 1 second, if you have code that takes 1 second to run, you will notice that. You will notice that. So even if these things are really fast, when you have an n cubed, yeah, you can get into some trouble. Okay, any questions about any of these so far? About O of 1, O of n, or O of n squared? And I'll drop this code in for you in Slack after we go through this. So don't worry about copying it all down. This is yeah, again, why when if you write your code and you end up finding yourself having a for loop and a for loop and a for loop, that's a warning sign, right? You should be able to see that and know, uh-oh, this is not so great. This is not so great. Step 4 will be to go back into it. You know, sometimes if you're just trying to get your code done, right? If you're on HackerRank and you're on a timer, or you're in your job and you need to deliver this by Friday and you have 5 more tasks to do, yeah, sometimes you're going to write triple nested for loops and you're going to get n cubes. But just keep that in the back of your mind. All right, this is something I'm going to have to go back to fix. All right, this is something on step 4 I might want to go back and improve. Okay, so these are exponentials. Okay, we have some that are less common. Things like O of 2 to the n. Here's a good example of, let's say you want to get all possible combinations. This is going to be O of 2 to the nth power. 2 to the 10th power is 1024. So we can do this, and we can the length of L should be 1024. Yep, because this is O of 2 to the nth power. Again, I'm going through this pretty quickly because these are less common. But anytime you're getting combinations, a list of combinations, you can have O of 2 to the nth. And here's an n factorial. N factorial, again, 10 factorial is 10 times 9 times 8 times 7 times 6 times 4 times 3 times 2 times 1. So this is also pretty bad. So we can do get all arrangements of animals. And we should get length of list. And we just do this. Of animals. This. Okay, it's chugging. It's taking a while. It's taking a while to run. Len of L equals, all right, this huge number, 3,628,800 different possible arrangements of our 10 animals. Okay, so our n factorial with just an input of 10 has already exploded to some huge amounts. Okay, so n factorials are particularly bad, but not so common. Okay, I think my computer's gonna die if I try to print this out, so I'm not gonna do that. Well, I have a MacBook Pro, and my computer's starting to cook already. Okay, last thing I want to do before we take a break is to compare these. Oh, actually, let's do a couple of things. Okay, so this is getting a length of our list, right? We called this O of n. The way we did this, we started with a counter of 0. For I in L, we incremented our length by 1, and then we returned the list length, right? Now Python and every language, actually, JavaScript, Kotlin, Java, everything has a function to get the length of a list, right, or the length of an array. These are generally going to be O of 1. So how does this work? How does this work? Rogelio, I think passwords with special characters are protected via hashing, which is sort of a different topic. But we're going to be getting into hashing in about 3 weeks or 4 weeks when we get into hash tables and blockchain. So so keep that in the back of your head, because we will be talking about that in a later topic. Yes. So the big O of len is going to be O of 1. So here's a question. How do we count n items in constant time? How do we count n items in constant time? Okay, is it Joe or Aljo? I'm just going to say Joe. Joe says, track the length of the list after every add or remove operation. Yes. Okay, yes. End minus starts. Not sure. But Joe, you're correct. So the way we do this is what's called amortization. Right? It's called amortization. What that means is every time you add an item to this list, every time you remove an item, you have a counter inside, right? It's something called metadata. So that means we have, like, in our class, we'll have something like storage equals this 1, 2, 3, 4, and we'll have count equals 4. And every time we add something to our list, we increment this by some number. Every time we remove some items from our list, we remove it by 3. Okay, so we're doing this count operation, right? But every time we add something, that's still going to be an O of 1 operation, right? Because we're incrementing something by 1. Okay, that's O of 1. We're increasing the storage by some amount. Now, when we get into data structures, we'll talk a little bit more about how much that costs. But generally, adding something to the end of an array, not the beginning, adding something to the end of an array is going to be O of 1. So altogether, we can do this in O of 1 time. And by keeping this metadata, by storing a counter, by amortizing our costs, we can turn this from an O of n operation to an O of 1 operation. Okay, so if this is our first optimization, if you want to take this from an O of n to an O of 1, we can do it by storing some metadata. How does it know the length at the beginning? Well, how are you declaring it? If you do something like x equals 1, 2, 3, that will probably, I think this is how it'll initialize the count, right? First, you need to allocate some memory, and in order to know how much memory to allocate, you'll need to count these items. So yes, declaring the initial array will be O of n, where you need to where n is the number of items. But then if you grow it, if you shrink it later, you can always get the length in constant time. Yeah, so beginning will be O of n to reindex everything. Because you'll need to, Python is interpreted, right? So this is all text. So first the computer is going to need to say, okay, we're having this variable x, we're setting it to something based on the square brackets. We know we're creating a list, and now we have 1, 2, 3 items in our list. So we need to create a list with 3 values in it. Then it'll need to read those 3 values into memory. So that's going to be an O of n operation. But once all that is done, now we can access this in constant time. And as you probably know by now, this is a very common operation, finding the length of an array. So we want to make sure that that these are O of 1s. Okay, I'll leave this code with you to play with yourself. It's break time, so I'll drop this in. You can play with it. This code is, I think, kind of cool to just see how the timing of various things work. But let's and we'll come back in 5 minutes, and we'll jump into binary search, linear search, and sorting. So let's take 5 minutes, and we'll come back. All right, that was 5 minutes. So come on and make your way back. And so I saw there's some questions in Slido that we can talk about. I also see, all right, so Ruben and Joe are talking about having to declare array sizes up front versus dynamic arrays. So yeah, in Java, well, actually I know C# mostly, but Java is very similar. In You can use dynamic arrays, but then there's also fixed arrays. So dynamic arrays, which we're going to be talking about again a little bit later in the course, are they handle a lot of these things for you, right? Things like first you need to allocate your memory. You need to allocate the size of your array, and then you can't go over it, right? This is because you need to reserve that space in memory ahead of time. When you have dynamic arrays, which is what Python allows you to do, it allows you to just create an array, add and remove things as you please without having to worry about the size. Now, it's not magic. It's not magic. And actually, when you go outside of the bounds of your initial array, it will need to resize it, which means you need to create another space in memory, copy everything over from the old array to the new space one at a time, and then free up this memory. That's going to be an O of n operation, and it's fairly slow. So dynamic arrays, they still have that complexity in it. It's just hidden. It's just hidden. And part of CS, part of what we're going to go over when we get into data structures, is understanding how these things work underneath the hood, how arrays work, how arrays versus dynamic arrays, or how hash tables or linked lists, how are these implemented, and what are the performance implications for using each of those. So great questions, and we'll be getting into these things throughout the a little bit later in the course. All right, so we have some questions here. How is O of n squared more efficient than O of n? It's not. Okay, yeah, O of n is better than O of n squared. Maybe I misspoke if a verbal typo, if I said otherwise. But if you look at this picture, this is O of n, right? Remember, this is how much time it takes compared to the size of the inputs. So this is O of n. That means performance. If you double the amount of items, it doubles the amount of time it takes to run, or it doubles the number of operations. Here, performance gets bad really, 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 really fast, right? So you hit 100 with just 10 inputs. So yes, n squared is going to be worse performance than O of n. Okay. How do procedural algorithms work? Procedural algorithms aren't too much different from regular algorithms. What they usually use randomness, right? They use some sort of randomness. An app that I'm building is actually a procedural flower generation algorithm, which I've been having a lot of fun with. But basically, is I'm taking some inputs, I'm processing them in somehow, and then I'm drawing a flower out of it. Things like, all right, what is the bushiness? Based on the bushiness, that's how I set my parameters, right? My leaf size and the space between the leaf nodes and things like that. We'll talk a little bit more about that later in the week as well. When you get into your build weeks, you may want to be you'll have a project where you might be able to use some procedural algorithms. So we can talk more about that as the week goes on. As computer science goes on. And how does metadata convert the complexity from O of n to O of 1? Again, we're amortizing this. So this means every time you add or remove from your list, you increment or decrement the counter that holds how many items are in your list. So that you're still doing the same number of operations, but you're just spreading them out, right? You're not doing them all at once. And also, once you do it once, you can store that data. So all you need to do is return the actual number. So I hope that helps. Does amortization come into play with caching? Caching is a little bit different. That's our topic for Wednesday. So let's save this question for Wednesday when we get into dynamic programming. But caching is a great way to improve performance, and it happens at all levels of computing, from as we're going to see, from writing like functions to browser caching, server caching, any type of local storage will generally, memoization, same as dynamic programming, or another word for dynamic programming. We're going to start covering that on Wednesday. So I'm glad you're excited. I'm glad you're excited about this, because we have all of these topics. I love it. I love it. I love the interest and the that you all have for computer science. We will be hitting all of these topics, I guarantee. But first, first things first. Let's jump into our main topic for the next 2 days, which is sorting. What is sorting? What is sorting? Sorting is very, very simple. Basically, you have an unordered list and you want to put them in order, right? Very, very, very simple to understand. This is a classic computing problem. Now, what makes it really interesting is that there's not a single best way to sort. When you say, all right, what's the best algorithm? There's many answers, right? There's many different ways to solve any problem. For example, we have this very simple problem, which is we have an unordered list of items. We want to put them in order, right? And how do we do that? There's many ways. There's many ways. We're going to be looking at 5 of them over the next 2 days, but there's many more than that. These are I would say the 5 most classic ones, the 5 most important ones to know. But if you want to go a little bit deeper, there's plenty that you can explore. Bogosort was the best. Best at I don't know what it's the best at. I can't even think of a joke. Bogosort is pretty terrible. For those of you who don't know Bogosort, the Bogosort algorithm says you shuffle your algorithm, you randomly shuffle it, and then if it's sorted, you return it. If not, you just try to shuffle it again, and you shuffle it again, and you shuffle it again until you happen to get a sorted return value. It'll work eventually, but it's quite inefficient. Okay, no Googling. Here's what we mean by that. All right, so your exercises for your homework are going to be to implement these sorting algorithms. So for today, you're going to be implementing bubble sort and selection sort for your homework. Now, if you Google this, if you Google selection sort in Python, you'll get some code. You can click this and get the entire thing, and you can copy paste it, and you can finish your homework in about 2 minutes, right? That's not the point of this assignment. That's not the point of this assignment. You want to try to implement these on your own. And the reason for this, the way you can think about these sorting algorithms, no, you're probably not going to have an assignment in your jobs to implement a sorting algorithm, and probably not even in an interview. I've never had an interview where it was just straight up implement merge sort, right? But what will come up is writing. Sorry, let me say this again. What this is good practice for is writing code that does more complex tasks, right? This is a very simple algorithm to understand, but it will stretch your coding chops a little bit. The way I think about this is like etudes in music, or scales, right? Anyone who plays an instrument, which includes myself, you've probably had to, before you started playing like concertos or pieces, you would have to learn your scales. That's what you practice, right? You practice your C major scale, then you practice F, you practice B flat, then you play your sharps, you play your majors, your minors. If you play guitar, you need to learn your chords, right? You need to learn this chord, this chord, this chord, this chord, and then you need to learn the chord progressions. You learn the 1, 4, 5, 1. You learn it in different keys, right? You need to practice these fundamentals. Now, do you perform this? Do you ever perform a scale, right? Do you ever get on stage and play a C major scale? No, of course not. But practicing these things will help you warm up. It'll help make sure you have strong fundamentals, and they will apply in many ways to every single piece that you may play or perform ever, right? So this is, if you want to get good at coding, these are really good things to practice. Practice these sorts. And when you're going through this, you also want to practice polya, right? Break these down into these steps. Number one, make sure you understand the problem. Number two, come up with a plan. The nice thing about these things is that step two is sort of taken care of for you, right? When we say implement insertion sort, we've come up with the plan for you, right? We're going to say this is what insertion sort is. We're going to tell it to you in words, and if you click here in the source, you can actually see we give you the description of these sorts. Like here is insertion sort. Here is the description of the algorithm, and your task is to implement it in code. Now, this is why we don't want you to Google, right? We give you all the information you need here, and there's a good amount of information. If you want a little bit more, you can Google and like maybe go to Wikipedia and see and read a little bit about these. That's fine, but I would say stop before you get to the part where they just tell you the code, right? Again, you can copy paste it and pass your homework, but again, that's not really the point. Like you're not getting anything out of that. And what we want to do is we want you to practice writing these more abstract algorithms to prepare you for interviews. And in that spirit, you're not going to have Google in an interview. So we want you to get some practice writing code, being okay with that uncertainty. Google is a very, very powerful tool, and we want you to make use of it. And last week, when you're doing Intro to Python, we told you, Google as much as you can. If you don't know how to do something, Google it, right? If you don't know how to set default args in Python, Google it. We want you to make sure that you learn to use that tool, but we also don't want that to be your only tool in your tool belt, right? Here we're going to give you some more tools that you'll be able to use when you can't find your problem on Google, right? That's the idea behind a lot of these things. Yeah, I love it. Yeah, we have an assortment of sorting algorithms for you to tackle these next few days. Okay, let's see, where were we? Before we get into sorting, why do we need to sort? Why is this so important? Why is it so important to sort? What is that bias? Well, the short answer to that is it allows us to search, right? Sorting is not as important as searching. Now, searching is something that is very, very important that we need to do all of the time. This little animals problem we wrote up here, has animal. This is very, very common. This is very, very, very common. We have a collection of things and we need to find something in it. What's an example? Well, we have a database, right? We have a database and we need to find all of the users, or let's say we have a user ID, right? Give me user 10. We need to find where user 10 is, retrieve that record, and pass it back. User 10 has 3 friends, which is user 400, user 3, and user 12. And we need to return all of those user profiles as well, right? These are all searches. As we saw, search is O of n. Search is O of n. Now let's take a company like Facebook, who has billions of users, right? O of n means that you have to do a billion operations in order to find an item. Now that takes a long, long, long time, even though Facebook has very powerful servers. If you have to do a billion operations just to do a single retrieval, that's going to take a long time. So we need to find some better way to search, and that better way involves sorting. Okay, now what does sorting get us? I know hopefully you watched a video on this, but if we have a sorted array versus an unsorted array, what can we do to modify this search function? What algorithm can we use to modify this search? We can reduce the size of potential results using binary search. Exactly right. Exactly right. Can someone describe to me in your own words, what is binary search? Describe to me the binary search algorithm. I see some starts here. We have some search from the middle, split in half, binary search. Okay, I think these are all correct, but give me a little bit more. Give me the algorithm just in words, and try to be just in a couple of sentences. Try to be complete. What I mean by that is, so I think you know step one of Polya, right? Understand the problem. It sounds like you know what binary search is. Now, what is your plan if we're trying to code it up? Planning can be a lot of things. One thing that we recommend is writing them out in comments, right? Like actually writing out like line by line. First, I'm going to need to do this, then I'm going to need to do this, then I'm going to need to do this. And then when you get to step 3, you're basically just filling in some code for your comments. Okay, let's see. Continuously divide, split in half, and keep the side that contains the value you're searching for. Repeat until value is found. Values must be sorted already. Eliminate half your options and do that again. Yes, yes, yes. Split in half, discard the half that's less. What you're looking for, repeat. Awesome. Okay, these are all great. These are all great descriptions. So if we have our list of animals, and let's just sort this right now. Animals dot sort, so like this. Animals. Okay, so we have our animals here, right? Now let's say we are looking for, we're looking for hippo. We know this is sorted, so we cut this in half. We have 10 items, so 1, 2, 3, 4, 5. We're going to say elephants. Is hippo greater than or less than elephant? Or is it equal? So it's not equal, and it happens to be greater. So we know that we can eliminate these, and we're just looking at this. Now I cut it in half again, and we get to hippo. We say, okay, is hippo greater than, less than, or equal to hippo? And it's equal, so we know that our item is in our list. Okay, can somebody tell me what the time complexity of binary search is? What is the time complexity of binary search? Log n, yes. Can somebody tell me what log n means? This is one of the trickier concepts. Natural logarithm, close. So, well, first of all, log is log base 2. I think natural logarithm is log base e, but we mean it when we in computer science talk about logs, we always mean log base 2. What does log base 2 mean? What does log base 2 mean? What does log mean, to be honest? Okay, great. Seems like there's a lot of questions here, which is perfect because that means I can do my, I still have a job. And you don't know everything already. Okay, so what does log mean? Log is, in order to understand logs, you want to understand exponents first. Okay, so if we say like, in Python, we can use ** to do exponents, right? So like 2 to the power of 4 equals 16. So let's say 2 to the power of 1 equals 2 to the power of 1 equals 2. 2 to the power of 2 equals 4. 2 to the power of 3 equals 8. You can see that here. 2 to the power of 1 equals 2, 4, 8. Equals 2, equals 4, equals 8. And we can also say 2 to the power of 10 equals 1024. All right. Now, if we do log, we can say log of 2 equals 1. Log of 4 equals 2. Log of 8 equals 3. Log of 1024 equals 10. No, I should say log base 2. Okay, do you see the pattern here? So the pattern is basically we're taking these exponents and we're just shuffling them around. So here, our first number becomes our base, right? This is the number. This is our log, the base of our number. The result is going to be the number that this is raised to, and this one here is going to be the result of the exponent. Right. So again, 2 to the power of 10 equals 1024. And if we do log base 2 of 1024, we get 10. Put another way, to calculate a log, this is the base to the power of the result equals this. Got it? We can also do log base 2 of 2048 equals 11. Log base 2 of 4096 equals 12, and so on and so on and so on. Now, one really big takeaway and one shorthand that you can remember if you don't want to memorize all of these logs. You know, again, powers of 2 you're going to find in computers. Powers of 2 are really important. And same with music, actually. Same with music. What I mean by that is you're going to see a lot of 2s, 4s, 8s, 16s, 32s, 64s. These are all powers of 2, and these are good to memorize. If, you know, just like you may have memorized your multiplication tables, like, you know, 3 times 7 is 21, 4 times 9 is 36, right? You can also remember 2 to the power of 5 is 32, 2 to the power of 10 is 1024, and so on. But, okay, why are these important? Because it can take really, really big numbers and turn them into smaller numbers. What that means is if you have 1024 users in your database or 1024 items in your list, all it takes is 10 comparisons in order to find the item that you're looking for. All right, so if you have 1,000 items in your list, your n is size 1,000. It'll take 10 operations to find it. Does that make sense? Okay, how do we prove that? So we have 1,024 items, right? Now we chop it in half, we get 512. We chop that in half, we get 256. We chop that in half, we get 128. Chop it in half, we get 64. Chop that in half, 32, 16, 8, 4, 2, and 1. And this 1 will either be our item or it will not be our item. But how many was that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 11. Off by 1, but that's fine. This is basically going to be, this is how many operations we need to do. Okay, so logs are great because they can turn 1,000 into 10. Here's another shorthand. Log base 2 of 1 million equals 20. Log base 2 of 1 billion equals 30. So if you're Facebook, if you have 4 billion users, all right, and you need to retrieve an account, how many steps is that going to take? You're not going to have to do 4 billion comparisons, right? All you need to do is 32 comparisons. Now, 32 is pretty quick. A computer can do 32 things in a blink of an eye. Doing 1 billion things will take a long time. Oh, sorry, this is not 32. This is 30. Doing 1 billion things will take a while, even for the most powerful computers. Doing 30 things will be pretty fast, even for a regular old computer. So this is why logs are important. This is why logs are important. And you can try this for yourself. I think if we have import math log, is it like 1, 2, 3, like this? Oh yeah, there we go. Yep. So log of 1,000 base 2 equals approximately 10. Log of 1 million equals about 20, and log of 1 billion equals approximately 30. Okay, so again, the big thing to remember is that when you're using a log, when you're using binary search, it can take a huge number and it can reduce it to a very, very manageable size. This scales very, very nicely. It's practically linear. It's practically linear. Now, O of n is, sorry, not linear, constant. It's practically constant time. Okay, so this is why sorting is important. This is why sorting is important, because it allows us to do binary search. Are there any questions about this? Okay, now most of you, it seems, I don't know, I don't want to say most of you because there's 84 people in this room and we have like 10 people answer. So at least the 10 of you who spoke up, I think understand. Hopefully the others of you have a decent idea of how binary search works. All right. Again, this is step 1. Step 2 is to write them out in comments. Now, step 3 would be to write it out into code, right? And we can I don't know, how are we doing on time? I think binary search is actually a pretty good exercise to practice on your own. This is something that I actually have had to implement in a job interview on a whiteboard, and the reason for that is because I wrote some code and then it worked, and I did it pretty fast, so I had some time afterwards, and then the question was, okay, this solution looks like it works. How would you improve it? And I found an unsorted list. I said, well, we could sort this and we can do a binary search. My interviewer said, great, can you code that? Can you code that for me? And I said, sure I can. And I did, and it worked out. Now again, think of these as scales, right? Think of these as etudes. Think of these as chords and chord progressions. These are really basic things that sure, you can understand how it works, but actually writing it out into code is a good exercise for yourself to make sure that you know how. And the way we would recommend that is to follow Polya. So understand how binary search works. Okay, I think you have a pretty good idea of that. Come up with a plan. Okay, plan might involve writing these out in comments and then fill that in with code. So let's maybe we can do something like let's try to write this quickly. I want to get to sorting before we run out of time as well. Actually, maybe it's better we should just jump into sorts. Okay, if we have some extra time at the end, I'll code up a binary search from my head. But before that, I want to get into sorting. This is something that I think you can go over in your on your own. Again, writing binary search I think is really good practice. Could I show you merge sort? Merge sort's for tomorrow. Merge sort is for tomorrow. And I think that's actually your homework. So I will not go over that today. But we'll definitely talk about that though. Today is a little bit packed. We're packing in a lot of stuff. But tomorrow we'll have a little bit more time to talk about some of this stuff. No worries, Andrew. Questions are always good. Okay, yep, searching. Why do we sort? Why do we need to sort? It's so we can do a binary search. Binary search is really powerful because it turns an O of n into an O of log n, right? Look, already this is a lot of stuff. Why is sorting important? So we can do binary search. Why is binary search important? Because we can turn an O of n into an O of log n. What does that mean? That means that we can turn a 1 billion into a 30, right? That's pretty fantastic. Okay. Unary search. There is trinary search. There is trinary search where you divide it into 3 and you do the same kind of thing. But binary search I think works pretty great. Okay, so let's jump into sorting algorithms. How should we go about doing these sorts? Well, we don't want you to reinvent the wheel here. We can. I think it's sorting is easy enough that you can come up with your own sorting algorithms, and I think this is a fun exercise. And if we have time tomorrow, maybe we'll try that out. I know we've done it in the past, and it's sort of hit or miss. Sometimes we get a group that comes up with a really cool sorting algorithm on their own, and sometimes it just kind of falls flat. But those are the fun. I think those are fun exercises if we get to it. But basically, since sorting is a well understood problem, since it's been tackled by many people, many brilliant computer scientists over the years, we have some pretty good algorithms for sorting. The first one we're going to talk about is insertion sort. Now, actually, before we go over this, let me ask you all a question. When you're playing cards, right? Maybe I think all of you have probably played cards before in your life, right? Like whether it's poker or Go Fish or some other thing, right? You get dealt your cards and you have a hand of cards in your hand, and then you want to put them in order. So can you all describe to me what is your algorithm for sorting your cards in your hand? Okay, insertion sort. Maybe you've read ahead and you've seen insertion sort. But can you describe to me, not saying the names, can you just describe to me how you do this? What is your algorithm in a sentence, in a 1 or 2 sentences? How would you describe how you sort items, cards in your hand? Like what is your algorithm for doing it? Okay, go through each card, and if it's less, move it to the left. Take the most out of place card, put it above or below a card of the same suit. Go left to right, sorting as you go through. Put the card in your right hand into the cards into your left, one at a time in order. Sorted cards on the left, unsorted to the right. And Megan, I presume you move cards one at a time from the right to the left. Organized by suit, left to right in order per suit. Make a pile on the left of sorted cards, go from left to right, moving cards into the sorted list as you go, unless they're naturally in the position they need to be. Okay, awesome. These are all great algorithms. These are all really great algorithms. It seems like most people do some combination of either insertion sort or selection sort. So today we're going to be talking about insertion sort. Now, what does insertion sort mean? Okay, so you have your hand of cards. Let's simulate this here. Let's simulate this here. Here's our hands. Let's say we have a 2, a 5, a king. Oh, these are already sorted. A 2, a king, a 5, a 9, a jack, and a 4. Let's not worry about suits right now. Okay, what insertion sort says is we start with a sorted list on the left, and we have an unsorted list on the right. Okay, here's our separator. These are still in the same hand. This is just for spacing purposes. Okay, now what insertion sort says is we take the first item from our unsorted list and we insert it into the correct place in our sorted list, right? So we take out our first item will be a king, and we want to put this here. We want to put this here in the right place, right? Next thing we do is we take out our 5, and where does 5 go? 5 goes here. Now we take our 9. Where does 9 go? We see it goes here. Where does our jack? Goes here, and our 4 goes here. All right, and we have a sorted list. We have our hand of cards is sorted. Make sense? So insertion sort, again, we call this insertion sort because we are looking through our list and then we're going to insert them into the correct place in our sorted list. Make sense? Okay, if that makes sense, let's try to code it. Let's try to code it up. So this is step 1 of Polya, right? Understand the problem. This is our algorithm. We can read this up. You can watch this video. These videos are really fun. I think you can watch this on your own. But basically, this is seeing the sort in action. Actually, we have all of the pseudocode here. So let's try this. Def insertion sorts. We'll have our list, and we'll have our item. Okay. Okay, so here's our plan. Here's our step 2 of Polya. Come up with a plan. Separate the first element from the rest of the array. Think about it as a sorted list of one element. Let's actually copy this list here. Okay, so here was our first item. It's 2, right? So we have our first element is our sorted list. For all indices beginning with 1, we can say this. So we'll have I equals 1 to say that our, okay, this is not here. This is just, we're not searching, we're just sorting. So if I equals 1, we know I equals 0 is already sorted, right? So now copy the item at that index into a temp variable. So we can do something like for I in range, we can delete this, for I in range of 1 and len of L, because we're iterating through each other item that's that is not in our that's after this. All right, so let's tab this up. Copy the item at that index into a temp variable. So we can say temp equals L of I. Let's call this list. Temp equals list of I. Now, what do we do here? So temp equals K in this case. So now we need to iterate to the left until you find the correct index in the sorted parts of the array, at which point the element should be inserted. What does that mean? That means we need to take our K, we need to scoot it over, or we need to basically check to see until the first item is smaller than the current item, right? So what is that here? We're just scooting it over here, and we already know that this is in the correct spot. So we're done. That means while let me see. We'll create a new, sorry, j equals I, while j is greater than 0, and let's see, temp is less than list of j minus 1. Then we swap it. So we have list of j equals list of j minus 1. And then, wait, I think I'm missing something. Here's our temp. Do I need to? All right, let's walk through this. Okay, while j is greater than 0, this says that if we get to the end, we just put it there. And temp is less than list of j minus 1. We move this over, and then we do j minus equals. Okay, then at the end of this, we find our correct index, and we can say list of j equals temp, and return list. Okay, let me make sure. Let me just try to run this before we make sure. This goes up here. Okay, what's our list? L. Let's do L equals list of range 100 and dot shuffle. Oh, actually, I need to import random. Import random. Random dot shuffle of L. Okay, here's a scrambled list. Insertion sort of L, and it works. All right, hooray! Okay, now that it works, I can confidently go. We can confidently walk through this code. Okay, what are we doing here? Copy the item at that index into a temporary variable. Iterate to the left until you find the correct index in the sorted part of the array, at which point this element should be inserted. Shift items over to the right as you iterate. Okay, so we have our. Let's start again. Let's start again. Here's our list. Okay, and our we'll write out variables in this let's do L equals this. Okay, now we have for I in range from 1 to the length of the list. So I equals 1. We're going to do temp equals k, right? We're starting here. Temp equals k. J equals I, so j equals 1. While j is greater than 0 and temp is less than list j minus 1. So this is saying while temp is less than, while this is less than this. Okay, now our first item, our temp is k. Our move 1 to the left is 2. So 2 is already less than this, right? So so we run through this. List equals list of j equals list of j minus 1. Hold on. Well, temp is not less than this. Sorry, temp is not less than k. Temp is not less than k. So temp is k, and the one previous is 2. So this doesn't even, we don't even do this at all. So now we do list of j equals temp. All right, so list of j equals temp, so this doesn't move at all. This does not move at all. So now we loop again. Now I equals 2. Temp equals 5. J equals 2. Now we check while j is greater than 0. J is greater than 0. List of j equals list of j minus 1. Now we have list of j is this equals list of j minus 1. So now we make this a k. And now we decrement this by 1. And we loop again. Now we see list of j, that's this k, is while list of, wait, did I do that right? List of j equals list of j minus 1. Yes. Okay, now we see while j is greater than 0. Oh, okay, well temp is 5. While temp is greater is less than this, and it's not. So now we finish. Now we finish. Now we say list of j equals temp. So our temp is 5, so we put 5 here. Right? And now we increment our I. And I is 3. And now we're looking at this one. Right? So now temp equals 9. Temp equals 9. J equals I. And we check this. Okay, so is temp, j is greater than 0. Is temp less than k? Yes, it is. So we set list of j equal to temp. So list of j equals list of j equals list of j minus 1. This is k. Now we loop around. We say is temp less than 5? It is not. So we set list of j equals temp, and we increment everything. Do you see where we're going here? Okay. Okay. Let's all right, people are lost. Let's start over. Should we start over again? How are we? What are we lost by? Let's walk through this again like this. Actually, let's do a simpler example. Actually, let's just use numbers. Let's say 5, 3, 1, 6. Okay. Don't worry about big O right now. Okay, so we have this list 5, 3, 1, and 6, right? We want to split this up into sorted and unsorted. So this first one is sorted, right? If we just have a list of 5, any list of one item is automatically going to be in sorted order. So we want this invariant. Everything to the left of this will be sorted. And don't think about this separation as like an actual physical space. All we're doing is we're marking it. All we're doing is marking it with this number. So we're saying right now I equals 1. Right? We start I as 1. So what that means is everything to the left of I is going to be sorted. So right now, this is all sorted. Right now, there's only one number to the left of I, and that is sorted, right? We start at 1 because we need to use this j minus 1. And if we do j minus 1 and we're starting at 0, we're going to get an error. So we want to start with one item that's already sorted, right? That's why we start from 1. Yes, that's confusing. It doesn't work that way. So that was just talking about cards. So that's why let's just use a number index to avoid that confusion. If you were to do that, you would need to write some code that evaluated that a j is greater than 9 and a q is greater than and so on. But let's not worry about that for right now. Let's just look at these integers, which are nice and easy. Yes, sorted list equals 5, unsorted equals 316. Again, everything to the left of our I is going to be sorted. So right now I is 1. Okay, now we're going to insert. We're going to take our first element, which is 3, and we want to insert it into the correct place, right? And by that, we mean we're going to slide it over one at a time until it's in its correct spot in the sorted list. So so we'll do that. We'll do temp equals 3, right? Temp is, this is the number we want to insert into the sorted half on the left. All right, and j equals the temporary item that we're sorting. So j equals I, which is 1. So this is the index of our temporary variable that we're sorting. Okay, now we need to do a null check. Sorry, a 0 check. We need to make sure our j is positive, because if j is 0, then we're going to get an error when we try to index an item by -1. So we start here. We say we want to slide this over until we get to the right place. So we're going to compare temp. Temp is 3. We're going to compare it to 5. Okay, now the question here is 3 before 5 or is 3 after 5? Now the way we check that is we see, is it smaller or is it bigger? So list of j minus 1, we're comparing it to the biggest number in our sorted list, right? So 3 is smaller than 5. So we know that 3 needs to go to the left of 5. So what we do is we slide it over, and that's what this sliding over is. So we can actually put this here. Shift items over to the right as you iterate. So we will list of j equals list of j minus 1. So we're going to overwrite this. Since we know we need to slide this over, we can overwrite this with 5. Now don't let this confuse you. Don't let this confuse you, because we still have our 3 here, right? We're trying to find the right place for 3, but we're still holding. Okay, so we slide this over by 1, and we decrement our j to 0, and now we loop. We loop in our while loop. Okay, so now we're going to exit out, right? Because we have this condition while j is greater than 0, and we know we're at the end of the list, so we can't slide it over anymore. So now our j is going to be 0, and we set this equal to our temp value, which is 3. And now we increment our I. Our I is 2. And you can see now everything to the left of this is sorted, right? 3 and 5 are sorted. 1 and 6 are unsorted. This is our unsorted half, and this is our sorted half. So now we loop again. Now we're looking at our temp. Our temp is 1. Our j, we're going to set it equal to I, and we're going to do this comparison again. So we're going to compare, we're going to see while j is greater than 0. Yes, j is greater than 0. While our temp equals 1, we're going to look to the left one item, j minus 1. So we're going to compare 1 to 5. Now 1, yes, 1 is smaller than 5. So we're going to put this here. Sets this to 5. And now we decrement j. Now j equals 1, so it satisfies this. And we're going to compare our list, our temp equals 1 to 1 to the left, right? So we're comparing 1 to this number, to 3. Is 1 smaller than 3? Yes, it is. So we need to shift it over again. So we set this one to 3. And we decrement our j to 0. Now we loop, and we see j is, this fails. So now we exit out of our while loop. Now we have j is 0, temp is 1, and we set list of j equals temp. That goes to 1. And now we iterate again. Now we loop again. We increment our I. We set our temp to be 6. This is what we're looking at. And our j to be 3. We're up here. While j is greater than 0, yes. While temp is less than list of j minus 1. Okay, our temp is 6. And our j minus 1 equals 5. So 6 is not less than 5. So we just, we don't even go into this loop. And we just set list of j equals temp, which it already is. And now we finished our iteration, right? We've gone through each of these items. We've inserted it into the correct place. And now our entire list is sorted. Now everything to the right is length 0, and we have 4 items to the left, and we know that this is going to be sorted. Awesome. Cool. Okay. Two more quick things. I see we're already a little bit over time. I want to get you out on time wherever possible. What is the time complexity of this function? Yeah, sorry, that was sorry, Josh. That was I think that was a confusing example, trying to mix the numbers and the letters. O of n, O of n. Any other guesses? We have an O of n squared. O of n squared. Okay, so how do we figure this out? First of all, we have an O of n. We have a this is our classic for loop, right? For each item in this list, we need to do something. Now within that, we have a while loop. Now we have a while loops are kind of the same as for loops, right? So we have a while loop inside of a for loop. Now how much are we doing here? What is the time complexity of this function? How many things do we have to shift over? Now again, it depends on the list, right? Best case is going to be we only shift over 0 times. Worst case is we have to shift over the entire array. Now the average case is going to be somewhere in the middle, right? That means we're going to have to shift over half of the array. So that's going to be, and the size of the sorted array is going to be also about roughly half of the array, right? Like when it starts off, it's going to be 0, size 1, and at the end, it's going to be the size of the entire array. So on average, we have to shift over half of the entire array, and then we also need to shift over half of that. So that's going to be O of n times n divided by 4, which equals O of n squared divided by 4, which equals O of n squared. We'll talk more about this tomorrow. I know we're running a little bit out of time. So think about this a little bit, but the correct answer would be O of n squared. I guess to be more exact, this would be O of big theta of n squared. This is the average case. I also think it's worst case. In worst case, it will be O of n squared. Okay, last thing before I let you go is, so your homework today is to implement bubble sorts and selection sorts. I think bubble sort is an easier one. Bubble sort is pretty inefficient, but it's pretty easy to implement. Basically, the algorithm behind this is you walk through your entire array. If you look at one item, you look at the next item. If they're out of order, you swap them. And then you go to the next, you swap them if they're out of order. Next, if they're in the right order, okay. And then you go swap it. And then you loop back to the beginning. And you keep going until you make it through the entire pass without having to do any swaps. And then you know your array is sorted. Selection sort is something else that you also might use when you sort your hand of cards. Basically, it's similar to insertion sort. You have your sorted on the left and your unsorted on the right. What you do here is you look through all of your unsorted items and you find the smallest item. And then you take that and put it at the end of your sorted array. Now you look through the remaining, find the smallest item, put that in your sorted array. You look, scan again, find the smallest item, put that in the sorted array. So that's a fairly simple algorithm that you'll be implementing in code. All right. If there's any questions, drop them in the help channel. We'll be keeping an eye. Your TLs will be keeping an eye on that, and we'll go over more of this stuff tomorrow. Tomorrow we'll look at some solutions for these. We'll do some more analysis, and then we'll start looking at recursion and some recursive sorts that let us get the values of n log n that we so crave with sorting. All right, cool. Thank you all. With that, I'll let you go. Hope to see some good questions in the help channel. Thanks for the lecture, and I'll see you all tomorrow.